we are still in mathematical methods for physics, solving differential equations, and I like to do things different. So this is the differential equation with boundary values, boundary conditions that I already solved in another video, and I'm going to do it another way. And I've done this way before in the past. I did a video on this, but it's so important, and I like to redo it, kind of refresh my memory, so maybe it'll be a refresher for you too. So we're going to solve this differential equation, second derivative of y plus 4y is equal to 0, with the boundaries y of 0 is -2 and y of pi over 4 is equal to 10. And we know the solution, okay? That's the solution once you apply the boundary conditions. But I want to do it a different way. And the nice thing about this is that by doing it a different way, with the solution already known, we can kind of like check and make sure it's working. Then when we get to another way to do it, another differential equation, we have more faith that our method's working. Okay, that's why we're doing it that way. So this is the finite difference method. Let me just go ahead and jump over and show you what this looks like. So I did use this code from my previous thing. So I'm just going to plot x from 0 to 10 and see the solution for y. And then we can use that curve when we get our solution to hopefully it's going to be the same thing. Okay, so this is the finite difference method, and it's extremely useful in quantum mechanics for two-dimensional, even three-dimensional quantum mechanics. It leads into the way you would do it with the eigenvalue problem, but we're not going to do that. We will use this later on to solve the wave equation too, so it's a pretty powerful method here. So let's just not worry about our differential equation. I'm going to put it over here. Let's put it over here so that we can remember it. Let's see, y double prime plus 4y equals 0. Y of 0 is -2. Y of pi over 4 is 10. That's what I have. Now I can erase all that stuff, because I will forget, right? So the finite difference method says, hey, let's take our values for x and y and give them finite values on the region that we're looking at. So suppose that I have the following solution. Here's x and here's y, and then I'm going to put that down there because I know what it is. And they're evenly spaced, so I just have some values up here for y. And so this is x1, it'd be x0, x1, x2, x3, x4. So I have five values. I only have 5 values, okay? That's my data point right there. And they all have x values, and they all have y values. Well, how could I find the derivative of one of these values? You know, they're data points, right? So they don't really have a derivative. You can't take the derivative like you normally would, but I can find the slope at any one of those points, and that is the same as the derivative. Okay, so let's suppose I want to find the slope right here. There's a couple ways to do this. What I'm going to do, you know, I could find the slope between these 2 points. I could find the slope between those 2 points. But just for safety, I'm going to find the slope between point 1 and 3, and I'm going to use that slope for the derivative at x2. And that's y. I'm sorry. This is x2. That's y2. These are all y values. y1, y3, y4. They have x values too. Okay. So let's calculate the derivative at y2. So I'm going to write this as y2 prime. That's the derivative there. And it's just the slope, right? It's just going to be, we can write this out. It's going to be y3 minus y1. That's the change in y values divided by 2 delta x, where delta x is the width between all my things. So that's that. That's not so hard, right? Now I can generalize that to the following. Y at the y prime I is going to be y I plus 1 minus y I minus 1 over 2 delta x, right? So that I can do any value if I know the y value ahead of it, the y value behind it, and I assume all the x are spaced out evenly, I can write that as my derivative. What about the second derivative? Okay, the second derivative is going to be the slope of the slopes, right? Well, we can do this a couple ways. I'm going to actually do this weird thing right here where I find the slope at the halfway point, okay? And then I'm going to find the slope here and then find the slope there. So I'm just going to write it out just to be clear. So this is y2. I'm going to write it with just numbers. So y of 1 0.5, y prime of 1.5. Now in this case, I could just take the difference in these two. So it'd be y2 minus y1 over just delta x. And then y of 2.5 prime is going to be the slope there, which is y3 minus y2 over delta x. Now when I find the slope of the slopes, the difference between these two is delta x. So I can take the difference between these. So I get y2 double prime is going to be equal to this. So y3 minus y2, and it's all over delta x. That's a delta x. This minus that, so it's going to be minus y2 plus y1, all of that over delta x squared. And you'll notice that that works out really nice, right? And so we can actually write this as y3 plus y1 minus 2y2 over delta x squared. Now I can generalize that to the ith element. yi double prime is going to be equal to yi plus 1 plus yi minus 1 minus 2yi over delta x squared. That's a super important equation right there. I mean, this one's important too, but if we have, in our differential equation, we didn't have a first derivative. We only had a second derivative, so we need that. Okay. So this says that if I go through all my data points, I can get an expression for the second derivative using the data point before and after it. Kind of a big deal, right? So let's use this in our differential equation. Let's use that in this differential equation. I don't want to delete that picture. I want to keep using that picture. So let's take this and say y double prime is minus 4y. So I'm going to write this as y double prime. Okay. So for the ith element. So that means yi plus 1 plus yi minus 1 minus 2yi over delta x squared is equal to negative 4yi. And this tells me something. It tells me I now have a differential equation, but it's using just values. I don't have to worry about the differentials, right? Because that's taken into account by looking at these before and after things. It's kind of crazy that this works, but it does. Let's solve this for this yi, but not that yi, because we're going to use them differently, which is weird. Okay, but that's what we're going to do. So I'm going to multiply both sides by delta x squared. And then I'm going to add this to both sides and add that to both sides. So I get 2yi, that's that one, it's on that side now, is equal to yi plus 1 plus yi minus 1 plus 4yi delta x squared, right? So I just added that to both sides, and I got that. I added that to both sides, and I got that. And then I'm going to divide by 2, and that's pretty easy to do. Now, what does that help? What does it do for us, right? Well, what I can do now is to pick some values for y. And to just pick, I can just start with any values that I want. I can guess. And then I can use those values of y to find better values of y. So I'm going to, for each yi, I'm going to go through and use this and calculate a better version, a better me, right? Better. And then I'll use the better versions to calculate a better version. And then I'll use the better version to calculate a better version. Better, best. Now, you can see that we do have a little bit of a problem here, because if I look at this data point right here and this data point right there, if I put in my y value for this and I look at this equation, here's yi plus 1, yi minus 1 doesn't exist. And same thing over here, I have yi minus 1, but I don't have yi plus 1. Doesn't exist. But you know what? That's fine, because these are special points anyway. They are our boundary values, right? We're going to keep those set. Keep them set. So here's what we're going to do. I'm going to make a Python list for my x values. And then I'm going to make a Python list for my y values. And then and I can start with whatever I want, as long as these two are fixed. I want those at my boundary points. So I can pick 0, 0, 0, 0. I can use those values to get better values, and I just keep on doing the same thing over and over again, and it's going to be great. So actually, I need 3 lists. One for my x values, one for my current y values, one for my new y values, and then when I calculate my new values, I set my old values to my new values, and I just keep on going forever. And if you don't like that, that's fine, I understand, because it's kind of crazy. But we already know the solution, so we can check if it works. Let's go ahead and do it. We have a lot of work to do. Lists, animated graphs. It's going to be great. Okay, I am switching to Python. So let's go back over here to Python, and I'm going to go ahead and start doing some stuff. Now, I gave all these weird values so that I wouldn't have to worry about what to change in the names and stuff like that. But the first thing I'm going to do is to make a graph for my other data points, and it's a G-curve, and its color is color.red. You can call it whatever color you want, color.red, and then I'm going to do this markers equals true. So there'll be a dot everywhere. You don't have to put that on there. I just like it. Okay, so now I need an x value to move through my points. So I do need a dx too. So let's say dx is just 0.1. I'm going to use something big, right? Because you can. And then I'm going to call this xp is equal to 0. That's going to be my x value that I'm going to move. Let's just move it from 0 to pi over 4. So I can do that while x is less than pi over 4. Print, I'm just going to print it, print x. Let's do this. Let's go ahead and make a list of x values. I'm going to call it x. X, it's an empty list. And so what I'm going to do is to put that in there. X equals x plus xp. No, this has to be in brackets. I'm going to add it to my list. And then I'm going to increase my value of xp. xp equals xp plus dx. And then when I'm done, I can print my list, x. That's all I'm going to do. And something happened. Markers, makers, that's why. It's markers. Markers. X is not a function. While xp. Okay, so you see here, I want to go to pi over 4, which is right here, and that's 0.78, and I'm only going to 0.7. It's not a huge deal, but what I'm going to do is just add one extra dx there. So watch this. If I say plus dx, and then we can run it again, and then I got that last element in there, and I think that's going to be a little bit better. Okay, doesn't have to be perfect. Doesn't have to be. And like I said, there's more than one way to make a list of numbers, but you do your way. Now I'm going to make 2 more lists, and I'm going to plot them. So I'm going to call one y now, even though we're not doing things in time, but we will later, and then y new, and they're empty lists. And I'm just going to add zeros to these. So y now equals y now plus 0, y new equals y new plus 0. And I need 2, and doing it this way, all my lists are going to have the same length. That's super important. You have to have them the same length. Now, I don't want to print this. Let's just go ahead and plot y now as a function of x. So I can go through the list and plot it. So for I in range, the length of x, and then so those i's are going to go from 0 to the end, and I want to plot it, f2.plot, xi, and y now I. And let's run that and see if it works. Okay, so there's all my y values are 0. I don't know why it does this. I think, okay, all my y now values are 0. That's not what I want. I want this one to be -2, and I want that one to be 10. So I need to move those. So I can just manually do that. So let's go down here. Once we make our list, I'm going to set my boundary conditions. Y now 0. Y now 0 is the first element in y now. I'm going to set that equal to -2. Y new 0, I'm going to set that to -2. No, equals. And then I want the last element, which is y now -1. -1 is how to reference the last element in a list, and that's going to be equal to 10. And then y new -1 is equal to 10. Let's run it again, and we should see that we are making excellent progress here. Okay, so now I have my boundary values set, right? You see that? So this one's over there, that one's over there, that's good. These are all 0, and that's fine. I'm going to change them though. Okay, so now what I want to do is to go through my list and use my finite difference to find new values. Okay, so how many times are we going to do this? Let's do it 100 times. So I'm going to use a counter, n equals 0, capital N equals 100. So while n is less than n, do the following. And I'm going to give it a rate of 10. So that way it's going to take time to do it. You don't have to do that, but that way we can see it, and we want to see it, right? Okay, so the first thing I'm going to do in this new in this loop is to thinking okay, so I'm going to make an animated graph. So to make an animated graph, you need to have your data as a list. So I'm going to call my data F2 data, and it's going to be an empty list. So I'm going to empty the list at the beginning of the loop every time I get there. Now I can just go through and use my differential equation to solve for my new values of y. So for I in range, let's get this up here, in range. Now I don't want to go through the whole list. I don't want to do the first one. I don't want to do the last one. So in the range 1 to length of x minus 1. So it's not going to go through the first one. It's not going to go through the last one. But I have that element I. Now I can calculate y new I. Y new I equals. Now I just type in my differential equation, or my finite difference here. I don't know if you can see. Yeah, you can see it right here. So yi plus 1. So y now I plus 1. Do you see how that looks? Isn't that cool? Okay, plus yi minus 1 plus y now I minus 1 plus 4 y now I times delta x squared, and all of that divided by 2. I think that's right. Okay. And that will just update all my y values. Now what I need to do is to go through and take my my new values and set them equal to my now values. So let's go through the list again. I can go through the whole list because I'm not going to change those endpoints anyway. For I in range, length of x, and then I'll just say y now equals I equals y new I. So I'm updating all my old values. You can't just say y new equals y now, because they'll set those two lists pointing to each other, and they'll always be the same and will work. You have to go through each element and change it like that. Now I'm going to go through, I'm going to plot, make my graph, my animated graph. So for I in, you could do this in the same loop, but I'm not. I like to do it in separate loops. Length of x, I want to add my data points to my F2 data list. F2 data equals F2 data plus xi y now, it doesn't matter, y now I, that's it. Now I can plot my data, so F2 dot data equals F2 data. That's going to make all the graphs. Now I can add my increase my value of n equals n plus 1. Whew, let's see if this works. I have a feeling I made a mistake. I haven't even saved this thing. That's kind of dangerous. Well, live dangerously, right? Let's just not save it. Look at that. You didn't really see it. Let's play it again. So every time I'm going through these elements and changing, they get better values. When they have better values, they get better values in the future. And so it kind of slowly approaches the solution that we know is the correct solution. And there you go. And then the thing I like about this, not only is it useful in other methods, but look how many data points I have. I have 1, 2, 3, 4, 5, 6, 7, 8, just 9 data points, and I get the solution to work. When we did this with the shooting method, we had a lot more data points, right? We had to adjust our initial slope a lot more times to get it to work really well. Here you don't have to do that. So that's that. That's the finite difference method with some animations. And again, you don't have to do the animations, right? That's just bonus stuff. It looks cool. Okay, that's it. I'll give you the link to the code down below. Talk to you later.